Hello. I would like to first thank Dr. Ernst Yu for introducing me, and also thanks to Dr. Han-Byeol Ju for inviting me to this summer school. And today I will be talking about some statistical and machine learning applications of the topological data analysis. And I guess many of the audience haven't heard about the topological data analysis before. So also a part of the talk will be just introducing the topological data analysis. Yeah, so I'll first start with some introductions. So I guess here in the computer science department, I think some of you have heard in topology in terms of in the context of the computer network. So in the computer network, the topology describes how the computers are connected in the network. So for example, like this kind of bus means the computers are like connected through a single line, and rings means that the computers are connected so that it forms a loop, and tree is just that the computer network structures has a form like a tree, and so on. And although the topology, the exact definition of topology varies in mathematics or computer science, but they have some common idea, and I think that's also shared the concept that topology describes how the local parts, so here, how the computers are globally connected together in the network. And that's also the main idea of the concept of the topology in the mathematics as well. And what we are doing with the topology is that topological structure provides some useful information. So here, this is a picture from a simulation data of the universe. So here, the individual yellow dots corresponds to a galaxy or gas or the dark matters. And when you look at the simulation in very large scale, then you might think that those galaxies are evenly distributed. But when you see the enlargement part, then you'll see some structures because of the gravity. Some galaxies are gathered together to make a cluster. And between the clusters, the galaxies will form some sort of edges, which is in cosmic, it is called the filament. And then there are some vacant spaces between the filaments and the clusters. So this kind of spiderweb-like structure is called the cosmic web in cosmology. And then this cosmic web structures give some idea of what was the initial conditions of the universe. So this topological structure tells you some information about the beginning of the universe. So this was just an example of how the topological structures from the data give some information, and also and for this, people are interested in using the topology in various fields, like this kind of astronomy, and also in biology, chemistry, in medical sciences, in material sciences, and so on. So, and using this kind of topological information in the data analysis is called the topological data analysis. But the problem is that topology is a very qualitative information, which means that topology describes how local things are connected, but it doesn't give you some numbers to describe, for example, like how things are better connected or how things are less sparsely connected, and so on. So the topology is itself a very quantitative information, qualitative information. So, and if you want to do some statistical inference or the applying that to machine learning, that we need some qualitative version of that, which means that we need some numbers to use that as a feature or use that to infer some topological information. So for making the qualitative version of the topological information, I will motivate with a piece of art. So this is a painting which is a very enlargement part of it. So imagine that you're standing at the very in front of the paintings, then you will see this kind of points. And then imagine that now you're stepping back from the paintings, then you'll see this kind of still points, but now you're in the back, so now you start to see some more global structures. And then when you step back further, then now you realize that that green dots actually corresponds to the part of a tree. And then when you step a bit farther, then now you'll see all the structures here. For example, here we have trees now, and you see some men and women, you see some dogs, and now you see some islands here. So the title of this painting is A Sunday Afternoon on the Island of La Grande Jatte by George Saha. And this painting is a typical example of pointillism. In Korean, that is 점요법, which means that you present the paintings by several points here. So that's also why when you see the paintings from the very close distance, then you will see only these points. But as you step further, then you will start to see some structures. And then if you imagine that you're stepping back very further, then all the structures will start to collapse because you're very far from the painting, so you will not see anything. So the idea of the pointillism is that the brain will process the points together to make some structures. So that's how the brain will work when you perceive many points together. And And that is also a bit similar to the idea of how we quantize the topological information, which is that you see the data in different scales. So first you see the data at the very close distance, and then you start to step back from each other, So you increase the distance, and then so by increasing the distance from 0 to infinity, then at some point you will see the topological structures, and at some point the topological structure will be collapsed. So the idea is to see the topological structures in different scales, and that's how we get the quantitative information from the topological structures from data. So in this talk, I will introduce how the statistical inference for the topological data analysis are done, and also the applications of the topological data analysis as well. So here, some of the work are mine and some of the work are from others, but I will just introduce them all together. Now, at first, I will introduce what the homology is, and I'll introduce how the statistical inference can be done on that. So for the homology, you can just think of how you are classifying the data according to its topology. So for example, here are the consonants of the Korean characters Hangul, and then you want to classify these consonants corresponding to their topology. And for doing that, we focus on the number of poles of different dimensions. So the number of poles, the pole of 0 dimension is the connected components, and the poles of dimension 1 is loop, and the whole of dimension 2 is void. And here the objects are in 2D, so we'll observe either the connected components and the loops here. So this is the result of the classification by homologies. So here, Betty 0 is the number of connected components here, and the Betty 1 is number of loops here. So for example, this one and this one are topologically same because when you rotate this one by 180 degrees, then you will get this one. So when two objects are equivalent by rotation, then they have the same shape, so they have the same topology. And when you count the number of connected components here, then it is obviously 1. And also they have no loops here, so this Giok and Neon falls into the category of beta 0 being 1 and beta 1 being 0. And for example, when you look at this consonant called Hill, then this has 3 connected components and 1 loop here. So this falls into this category. So by doing this, the objects are classified by homologies. So the objects that are falling into the same category means that they have the same whole structures. And relating to this, I will briefly introduce the statistical inference for the cluster trees. So the problem here is as follows. So we have some data like this, and then we want to cluster data, which is also classical problems in statistics and machine learning. And for doing that, like if you want the clusters to describe very local and detailed informations, then you will probably want to cluster points into 3 groups like this. So this clustering describes the very local and detailed informations, and it's like you're looking at the data at very high resolutions. So that corresponds to you're looking at the data from very close distance. And if you want the clusters to describe whether global and rough informations, then you just probably want to cluster everything into 1 group. So compared to this and this, the high resolution is more like you're looking at the individual trees, but low resolutions is more like you're looking at the entire forest. And also there's some middle stage like this as well. And now, as you have seen, you can create cluster results from different resolutions. And then those clusters from the different level of resolutions have some natural inclusion relations. So this yellow cluster and red clusters are a subset of these orange clusters, and also all the smaller clusters are a subset of these sky blue clusters. So these clusters from different levels have the inclusion relations, and this inclusion network can be represented as a tree like this. So here the yellow clusters and the red clusters are merged into orange one, and the orange one and the blue clusters are merged into sky blue one. So from this clustering results from different resolutions, we can get the cluster trees like this. Yeah, so that's how we think of the some mathematical object that is called the cluster tree. So to be specific, the cluster tree is the mathematical concept of the cluster tree is the network of the connected components of the upper level sets by varying the level by varying the levels. So for example, when you set the lambda is 0.5, so this is the level, and then this function is the density function. So when you fix the level lambda is 0.5, then you look at the upper level set, which means that you look at the points where the function values are larger than 0.5. So the upper level set corresponds to this one. And then you look at the connected component of this upper level set. So here we have we only have one component here. So this is the connected component here. And then you retrieve this connected components of the upper level set for all possible levels here, from level being from infinity to 0. So for example, like when you decrease the level to be 0.4, then now you have these 2 connected components here. And then now when you decrease the lambda at 0.3, then you have one connected component here like this. So for each individual levels, you will have connected components of the upper level sets, and then to visualize and also to conceptually understand, you represent each connected component as a point. So here, so here you represent this connected component as a point here, and then you represent this connected component as 2 points here and here, and then here. And then when you repeat this, then the points which is actually corresponding to the connected components, when you collect those points, then those collection of points will have a structure of a tree. Because the individual points corresponds to the connected components, and the connected components have the inclusion relations. So when you visualize that, then you will see a structure that looks like tree, like this. And then in terms of the statistical inference, a matter of interest is that you don't directly observe the density function itself, but you will just, in many times, you will just observe sample points from that. So you cannot directly get the density function, but you will have only its estimates. So for example, from the density estimate, when you make the cluster tree, then you will have this kind of small leaves as well, which is possibly from the sampling effect or noise. And then what you're interested is that you'll be interested in differentiating this kind of leaves that are possibly coming from noise versus this kind of structures that really lies in the underlying density functions. So how you do that is by using the confidence set. So here the confidence set is the set of cluster tree where the true tree from the true density function is captured in this confidence set with the probability of say 95%. So that means when you compute the confidence set for like 100 times, then for 95 percent of the times you will capture this tree from the true density function. And this bar is some sort of a visualization of the confidence set. And then what we do with this confidence set is that we can use this confidence set to determine that these leaves are, so these leaves have the length that is smaller than this confidence tree. Then we would say that, okay, these leaves are not important, so these leaves are possibly from the noise. And then these leaves have length that is larger than this confidence set. Then we will say that, okay, these leaves are statistically significant, which means that when you compute the cluster tree for like 100 times, then for more than 95% of the times, we will see these leaves that are in the bold color. But these small leaves don't have that kind of guarantees. Yeah, so for computing the confidence set, we use the kernel density estimator. So this kernel density estimator is just like a density function that is computed from the data. And then we let the confidence set to be a set of tree that has this this empirical cluster tree as center and radius t sub alpha that is also computed from the data as well. And then this confidence set has this probability guarantee that this really captures the true cluster tree with probability 95%. Yeah, so this is an example of how the confidence set for the cluster tree is done in some simulated data. So for example, if you have this data given and then compute the cluster tree, then you have this kind of tree with this kind of small leaves as well. That is mostly coming from the sparsity of the topo points here. But when you compute the confidence set, then we can conclude that these small leaves are actually not topologically significant, and we'll be able to recover the tree structure that has two leaves like this, which actually corresponds to the true cluster trees from the density functions. Yeah, so that was the statistical inference for the homology, and then I'll move on to the persistent homology. So now I have introduced the homology as counting the number of holes, but to apply that to data analysis, when we only have the finite data points, have some problem, because for example, if you have this kind of circle here, then this has one connected component and one loop here. But when you have, for example, suppose you have observed 100 points from this circle, then you will have 100 connected components and 0 loop, because when you have finite points, that is not possible to form a loop. So no matter how many points you observe from the data, you'll never be able to recover this loop structure. And then the remedy of this is similar to what I have presented by the paintings. So here, the one reason that you are not able to observe the loop structure is maybe just that you are looking at the data too close from it. So you just see the individual points, and to see the trees or men or dogs, then you might have to step back a bit further. So that's some sort of idea for doing this. So suppose you are looking at the data very close to the monitor, then you'll see all the points that are clearly distinct. And then imagine the process that you're stepping back, then the points will be starting to be blurred, and then those blurred points will be merging together. So we can think of this process as attaching a disk of radius r, and then increase the radius r, attach the disk of radius r, center at each data point. and then you increase the radius r from 0 to infinity. Then, for example, when the radius becomes 0.5, then now you'll see that a loop is formed here. And then as you increase the radius further, so for example, like if the radius becomes 1, then you'll see that the loop structure is collapsed because the inside hole is filled. So as you change the radius from 0 to infinity, this loop structure appears at 0.5 and disappears at 1. So this 0.5 is called the burst time, and this 1 is called the death time. And then you collect the pair of burst time and death time 0.5 and 1. And you repeat this for all other possible quadratic components and loops, and also higher dimensional homology as well. And then this collection of points is called the persistent homology. And then for easiness of the statistical analysis, we do a little bit of tweak here. So before we have considered a collection of disks with radius increasing from 0 to infinity. So, and similar process can be done if we have a collection of sets that are increasing. So instead of this, what we can do is that we fix some function here, and then we decrease the level, and then we see the super level set of this level. So here we use the current density estimator. So here we use the current density estimator, and then we start from level infinity, and then we decrease the level to 0. And then, for example, at level 0.25, then you'll see this kind of super level set. So super level set is the set of points whose function value is larger than 0.25. And then, for example, when the level reaches 0.15, then you'll see this loop. And then when the level decreases down to 0, then you'll see that this loop disappeared. So for this case, the burst time is 0.15 and the death time is 0. So this triangle corresponds to this loop structure. And then you do this from the current density estimator, we can produce this persistent homology similarly as well. And then now we can see that when you look at the persistent homology of the underlying manifold and the samples, and now they look quite similar to each other. So in this kind of sense, the persistent homology is in this sense robust, and then the persistent homology of the underlying topological structure can be inferred from the persistent homology of the finite samples that are from the topological structures. And to do the statistical inference, we need some. So for doing that, we need to say two persistent homologies are close, either close or far. So that is saying that we need some distance between the persistent homologies. And what we are doing, and then the one common distance to use is the bottleneck distance. And in fact, this bottleneck distance is analogous to the Wasserstein distance with the infinite norm. So how we do that is that, okay, so we have 2% homology here, and then we also think that there are infinitely many points on the diagonals as well. And then what we are doing is that we do some matching here. So here, the gamma corresponds to a matching from 2% homology. So here, the circle has 1 point here, and the 100 samples has these 4 points. And then, for example, we can match these yellow-green points to the green points here, and then there are infinitely many points on the diagonals as well. So we can match these points to the points here as well. Then say this matching is gamma 1. Then now we measure the infinite distance between the matched points, where infinite distance means that you measure the horizontal difference and the vertical difference. So for example, the infinite distance for this matching is say 0.1 here, and then here the infinite distance of this matching would be also say like 0.1. So, and then you take the supremum over all matched points here. So that will be 0.1. And then you do that for all possible other matchings as well. So for example, this time you match this point with here and this point with here. Then for this case, the infinite distance between these 2 points will be 0.15. So here and then when you take the supremum over the all blue arrows, then you get 0.15 here as well. So you did this for all possible bijections from one person homology to the other person homology, and then you take the infimum. So here the infimum is coming from the matchings that corresponds this point, this point, and this point, this point, and that distance, and that was 0.1. So now so now here the 0.1 is the bottleneck distance between these person diagrams, between these two person diagrams. And then what we do by the statistical inference of the person homology is, again, you do some sort of a confidence set as well. So here the confidence set is a set of random persistent homology that captures the person homology of the underlying data with probability 1 minus alpha. So for example, here, this is the person homology of the circle. And then you consider a set of person homology that has the person homology of from the data points as its center, and then radius C sub n. So these are the set of random person homology, and then this being the valid confidence set means that this random set of person homology will capture the person homology of the circle with probability, say 95%. And when you visualize this set of this confidence set, then this looks like this. So here the points are corresponding to the Pearson homology of the 500 samples, and then this is the set of Pearson homology whose boundary distance is within C sub n to this Pearson homology. Then how does this set look like? Is that when you take any Pearson homology from this confidence set, then it has points that may not be exactly same as this, but their locations are similar. And in particular, their locations are similar in that the random Pearson homology will have one point in this rectangle and another point in this rectangle, and then another point in this rectangle, and so on. So here the rectangle has center as this point and side length as 2 times Cn. And then it's like if you have the point from this confidence set, then you will have you may have some perturbation of the location of this point, but that perturbation is limited to this box. And then you might have noticed that here I have colored this pink box and the gray box differently, where the difference is from that these pink boxes don't overlap with these diagonal lines, while these gray boxes overlap with these diagonal lines. So that means that the points that appear in this pink box is always off diagonal. So it's like you will always observe these points, but these gray points don't have that kind of guarantees because they overlap with the diagonals, so they can actually appear on the diagonals. So in that kind of sense, we can say that when you draw so here, for example, the C sub n was 0.05, and then when you draw the line, that is vertically 2 times Cn from the diagonal line. So here vertically 0.1 from the diagonal line. And then all the points that are above this pink shaded area are statistically significant, meaning that when you compute the empirical Pearson diagrams like 100 times, then you will observe these points more than 95 times. But these points don't have that guarantees. So in this kind of sense, in the Pearson homology, you can differentiate the statistically significant topological features versus topological features that are not significant. So these points can be just from noise, or can be just that the homology is not strong enough to be observed from the finite number of samples. And these are just an algorithm for computing the confidence band for the Pearson homology. Yeah, and yeah, sorry for the interruption. So I will just go over the applications in machine learning quickly. So roughly saying that the machine learning is that you are inferencing your parameters using the gradient descent. And so for, yeah, sorry. And so for doing that, and to help the machine learning with the topological data analysis that are usually done in two ways. One way is that using the topological data analysis as additional features to your data. And another direction is that the loss functions, the loss function that you use when you compute the gradient descent, this loss function is accompanied with the topological loss terms, so that the loss function reflects the topological similarities of your data and your model. Yeah, so the first one, I will talk about how you can featureize the topological data analysis, how you can featureize the data with topological data analysis. So one way of doing this is the persistent homology. So when you have this persistent homology, then it's like you rotate the data. You rotate the persistent homology with 45 degrees clockwise. So you look like this, and then for each individual point, you draw a right angle triangle of 45 degrees. So you have this triangle, and then you think of this as a function. So each individual point will generate individual functions, and then you compute the pointwise maximum, which corresponds to this blue line, and you can view this as a function from R to R. So this is called the first landscape function, and then you compute the second pointwise maximum, which in this case is the minimum because we have only two functions. So that corresponds to this black line, and this is called the second landscape functions. So you have, and you do third pointwise maximum, fourth, fifth, and so on. So this collection of functions are called the persistence landscape. And then there are some applications using this, but I will just go over one application quickly. So here is applying the persistent landscape to build the topological layer. That means that when in the deep learning, the output layer is a function of input layer, and then what we are doing here is that we build the layer so that the output layer reflects the topological information from the input layer. So we do that by passing the input to the compute the persistent homology from the input data, and then compute the persistent landscape, and then by using the differential map, we collect output vectors here. And then by using this layer, we have some improvement in the classification result. So for example, here the NLP is the multi-layer perceptron, and the NLP plus P is the NLP accompanied with the topological layer. And then you can see that the accuracy is like greatly increased, and also the same phenomenon is observed for CNN versus CNN plus topological layer. And also when you add the topological layer, then you can see that the variability of the model greatly decreased. Yes. And then another thing is that you can just consider the topological terms when you build the loss function. So for example, like here, this is a typical autoencoder. So you have input data, and then you have a deep learning layer structure like this. So when you compare the input and the reconstruction for them to be similar and to consider reconstruction loss, then this is a typical autoencoder. but you can also additionally consider the topological similarity of the input data and latent code. So you did this by computing the distance between the input data and latent code, and then you're training along the direction that this input data and the latent code are also topologically similar as well. So by doing this, so here the original data is a collection of 10 spheres, which is of 100 dimensional, which is of 100 dimension in 101 dimensional Euclidean space, surrounded by one big sphere. And then all the other dimension reduction method don't really represent this kind of information that one big sphere is containing the others. But when you add a topological loss term, then this global topological structure is more or less preserved in the representation space as well. And this is just like the tools for, just like the libraries for comparing the topological data analysis. And yes, so this is my end of the talk.